Assalamualaikum. Today for PHY380 video presentation, we are going to present about infrared radiation technology, which is night vision. I'm sure most of us are familiar with night vision that is commonly used in the military sector. However, night vision are also used in a lot of other sectors such as healthcare and for safety also. Before we begin, I would like to introduce our team members. Our team members consist of 5 people, which is starting from Raja NURSYAFIQAH binti Raja Muhammad Syukri. Second, we have NURUL HUMAIRA BALQIS binti MOHAMAD ZAKARIA. Third, we got SITI KHADIJAH GAPUL binti AWANG ABBAS. Fourth, ZULAIKHA HUMAIRA binti JOHARI. And lastly is me, MOHAMAD FAHIZI bin JAMAL. Now, without wasting any time, I will pass my presentation to Raja NURSYAFIQAH binti Raja Muhammad Syukri to proceed to explain a little bit of this topic.
Good morning everyone. Today we will explore a technology that allows us to overcome a natural human limitation, which is our inability to see in the dark without technological help. Night vision works by turning invisible signal, specifically infrared radiation, into clear image that our eyes can process. While this technology was once strictly for military use, it has now evolved to protect and serve everyone in various fields, from security to healthcare. Now, let's look at why this technology is a game changer in the real world. It goes far beyond just green googles in movie. First, it allows for operation in total darkness. Unlike our eyes, infrared technology detects thermal energy or heat from object and people. This means you can see clearly in 100% darkness without any external light. For example, a rescue team can use it to find a lost hiker in the pitch black forest just by tracking their body heat. Second is atmospheric and weather penetration. Infrared waves have longer wavelength, allowing them to cut through fog, smoke, and rain. A great example is firefighter using infrared camera to navigate through thick smoke to find trapped victims inside a burning building. Third, it has revolutionized security and surveillance. It used for effective perimeter monitoring to spot intruders or suspicious activity instantly. Because these devices are now available in both low and high cost model, even small businesses can use this technology to protect their property at night. Finally, there is medical imaging. Advanced material now allow for deep tissue imaging that letting the doctors see through biological layer with high precision. For instance, it can be used for non-invasive diagnostic to monitor blood flow or detect tumor without immediate surgery. In short, from saving lives in disaster to protecting our homes and improving healthcare, infrared technology is truly indispensable.
Assalamualaikum and good day to everyone that's watching currently. My name is SITI KHADIJAH ABBAS and I'll be your presenter to talk about detailed exploration of our current topic, where I'll be talking about green night vision and thermal imaging. So without further ado, let's get right into the first slide. So first slide, which is image enhancement or optoelectronics, is the slide where I'm talking to you guys about the classic green night vision that we usually see in spy movies or even military movies. So how does this exactly work? Well, I'll explain. You guys can refer to the diagram that I've attached for a further understanding. So first is the light amplification, where it will get the tiny amount of ambient light such as moonlight, starlight, and even infrared light. Second is the photocathode, where the photons will hit a sensitive plate that will convert those photons into electrons. The third one will be microchannel plate, which is the MCP, where the previous electron will fly into some kind of disc with a lot of teeny tiny holes, where then will hit a wall, creating this thing called snowball effects. So the previous electron will be multiplied by a number of thousands. Last but not least is the phosphor screen, where the previous electron will hit a screen that glows in green and hence create a bright image of the dark screen. So fun fact, Why does it glows in green instead of yellow or red? It's because our eyes, the human eyes, are more attuned to see more shades of green compared to the other colors. So if we see using green night vision instead of red night vision, hypothetically, the green night vision will produce a more enhanced image compared to the red night vision. And secondly, it's also because of reduced fatigue, because our eyes could go a more longer period of time looking at green screen compared to looking at other color of screen without getting too tired. That's all for the first slide. And now on to the second slide, where I'll be talking to you guys about thermal imaging, which is also called as radiometry. So interesting enough, this one doesn't require us to use light like the previous green night vision, but instead it requires us to use heat. So a fun fact again, all objects around us emit some kind of radiation, heat radiation. Doesn't matter if it's cold or if it's hot. Even ice cube that is 0 Celsius or 273 Kelvin above absolute zero, also absolute temperature, so it will also emit some kind of radiation that could be detected by the thermal imaging. So okay, let's talk about how this exactly works. So first is heat signatures, where a special lens will focuses on the IR radiation that will be emitted by all kind of objects. Second will be the phase array, where a detected element, which is also called as microbolometer, will create a temperature pattern that is called thermogram. So a microbolometer, to put it simply, is a grid of tiny thermometers, where when the IR radiation hit these tiny pixels, it will heat them up, and then this heat will change the electrical resistance, and this difference will be measured and then will be converted into thermogram. And last but not least is the data processing, where the thermogram will be converted into electrical impulses that will be sent to a screen display, where different temperatures are assigned to different colors. So like there are two types, white hot or rainbow palettes. So white hot are usually used by the military because our brain could make up human figures better in grayscale, and the rainbows for the engineers and the doctors, because for engineers they could detect tiny temperature leak because of its high contrast, and the veterinarian could detect the inflammation in the horse leg. So that's all from me for the second slide. Thank you.
Next, we will move to the scientific instrumentation and application of thermal technology. The first one is thermography. Thermography is primarily used in the medical field, which is to detect the inflammation or circulatory issue by visualizing the heat variation on the skin surface. And the second one is drone and thermal imaging. This is a vital tool for search and rescue. It provides the aerial view that helps team to locate the missing people by identifying their heat signature from above. And the last one is night vision goggle. These are often mounted on equipment or helmet to detect the heat signature of targets and allowing for high precision monitoring in the total darkness. Now, I will explain more detail about the scientific instrumentation and application concept of infrared night vision technology. The first one is thermography system. The main instrument used is the microbolometers. A microbolometer is an infrared detector that sends infrared radiation emitted by the objects. When it absorbs the infrared energy, it will cause a change in temperature, which results in a change in electrical resistance. This signal is produced to form a thermal image, also known as a thermogram. Thermogram shows the temperature distribution or object. In addition to microbolometers, some infrared systems may also use the temporal array. A temporal array works by converting the infrared radiation into voltage signal based on temperature differences. However, thermophile arrays are generally used for simpler temperature sensing application, while microbolometers are more commonly used in advanced thermal imaging systems due to the higher resolution and sensitivity. Next, infrared thermal imaging is widely used in drones. Drones equipped with thermal cameras that can detect the heat signature from human or object even in complete darkness. This makes them very useful for search and rescue or environmental monitoring. For night vision Google, a different technology is used called image intensification. This system amplifies very low level of light and converts it into visible image. The image is displayed through a phosphor screen, usually producing a green image that allows the clear vision in dark environments. In conclusion, infrared night vision technology uses different instruments depending on their application. Thermal imaging uses microbolometers, drone use thermal cameras for aerial detection, and night vision goggles use image intensifiers with phosphor screen.
Thank you, Humaira, for the amazing explanation. Now, I will explain about the example of real-world implementation in night vision. First, we have automotive and transportation that use infrared sensors in advanced driver assistance systems, where it helps the drivers to see potential hazards in low visibility conditions such as fog, rain, or nighttime driving. Furthermore, thermal cameras in vehicles can detect pedestrians, animals, and other obstacles, reducing the risk of accidents. The second one, we have security and surveillance. In this sector, they commonly use infrared technologies such as thermal cameras to detect intruders in low light or total darkness. It can also be used to monitor the movement of individuals in areas with restricted areas or in large outdoor spaces such as border or warehouses. Since thermal cameras do not rely on visible light, they can function effectively in any lighting condition, providing 24/7 surveillance capabilities. Lastly, night vision technology has been used in healthcare sector too, to improve patient care and medical procedures. For surgeries, they will use night vision systems during minimally invasive surgeries, allowing them to see in low light environments and perform precise operations. Other than that, neonatal care will be much easier as doctors may monitor premature infants in low light conditions without interrupting their sleep. Now, let's proceed to the potential benefits of infrared radiation technology. First, it will enhance your vision in low light conditions because night vision devices allow you to see clearly when natural light is scarce, no matter whether you are exploring the wilderness, conducting surveillance, or simply navigating your surroundings at night. The second pros of night vision is it will increase safety and security. For example, law enforcement agencies, military personnel, and security professionals rely on night vision equipment to detect potential threats, conduct covert operations, and ensure the safety of communities. Additionally, night vision technologies also helps in empower homeowners to protect their property and loved ones after sunset. Lastly, night vision is crucial in search and rescue operations where it can help in locating missing persons in remote areas or responding to emergencies in the dead of night. This will lead to the improvement of chances of a successful mission. Moving on to the challenges associated with night vision technology. While this equipment is transformative, it is not without significant hurdles. We can categorize these into three primary areas: human factors, performance drawback, and cost and complexity. First, let's focus on the human factors. Extended use of these devices often lead to significant eye strain and physical fatigue. Furthermore, the added weight of the helmet setup can be physically taxing over long mission. Perhaps most critically, users often experience disorientation when transitioning from the high contrast view of night vision back to natural, unaided vision. Second, there are inherent technical limitations. Night vision devices are highly susceptible for bright lights, which can cause temporary blindness or wash out the image. Additionally, for systems that rely on active illuminations, there is a major tactical risk, which is a technologically capable enemy can detect that light source before our own warfighters even spot them, effectively compromising our position. Finally, night vision technology faces issues of cost and complexity. These systems involve sophisticated hardware and software, which makes them expensive to acquire and technically difficult to maintain. As you can see on the picture below, the price point for these devices varies drastically, from $100 for consumer-grade digital optics to over $10,000 for high-end military-grade analog systems. This wide range makes specialized equipment less accessible and requires extensive training to operate efficiently in the field. Now, I will pass my presentation to Zulaikha.
The future development and innovation for infrared radiation technology in night vision are: first, flexible spherical organic photodetectors. Traditional shortwave infrared spherical night vision relies on rigid, heavy, and expensive inorganic semiconductors. Future hardware is moving towards shortwave infrared organic photodetectors, which is spherical PDS, that utilize N-type small molecular semiconductors. These materials offer core advantage of lightweight construction, mechanical flexibility, and low cost, large area resolution processability for wearable electronic sensors. Next, sub-reference pixel miniaturization. To bypass the strict size, weight, and power constraints of modern night vision systems, research focused on shrinking focal plane array pixel size. By pushing engineering toward thermodynamic and quantum limits, developers are creating smaller pixels to achieve megapixel level high resolution on incredibly compact physical sensor footprints. Next, nonlinear silicon metasurface, which is up conversion imaging. Instead of using conventional, heavily cooled infrared electronic sensor arrays, future night vision can utilize nonlinear up conversion to convert infrared light directly into visible bands. By breaking in-plane symmetry on silicon platforms, a high-Q quasi-bond states in the continuum resonance is achieved. This dramatically enhanced third harmonic generation, translating arbitrary IR image directly into high-fidelity visible light with a sharp spatial resolution, which is 6 times 10 power of 6. Lastly, in-sensor machine vision and optoelectronic membristors. To advance smart night vision and autonomous military or security systems, computing is moving directly to the sensor. A newly developed plasmonic optoelectronic memristor using tellurium nanowires and gold nanoparticles enables a fully light modulated vision system. It's operating via localized surface plasma resonance. It creates an all-photonic wide or iris scheme to compute and track motion in complete darkness, achieving a 91.4% moving object recognition accuracy.
In conclusion, while infrared night vision technology is a powerful tool that enhances security and improves healthcare, it is not without its challenges. As we have seen, current devices often face significant hurdles, including eye fatigue for the user, vulnerability to bright light interference, and high costs associated with complex hardware. Furthermore, the reliance on active illumination can sometimes create tactical disadvantages in high-scale environments. Despite these obstacles, the future of the field is bright. By moving toward ultra-compact, flexible material and flat optical surfaces, we can eliminate the need for heavy, cumbersome electronics. When combined with artificial intelligence embedded directly onto miniaturized sensors, next generation technology will be able to process thermal motion in total darkness with minimal power consumption. Ultimately, infrared technology does more than provide a cool gadget. It allows us to perceive a hidden side of our world. By transforming invisible energy into clear, actionable information, we are not only improving our ability to see in the dark, but also ensuring that this technology becomes more accessible, efficient, and effective for everyone. This is our references. We use at least 10 different references from the article on the internet. And this is the end for our presentation. Thank you for your attention. Goodbye.